around to figure out what to do with the recordings, but we are recording now.
Okay.
Yes. Okay.
Okay, great. So hi everyone. Thank you so much for inviting me to speak. I'm going to talk about churn bands and the geometry of twisted bilayer graphene. So I'm going to begin by just talking about the continuum model for twisted bilayer graphene to remind everyone what the band structure is and how to think about the system. So we think about two graphene layers that are twisted relative to each other, and they form a long wavelength Moiré pattern. So here the red dots show the AA sites, and they form a triangular lattice. The AA sites where the two, the A sublattice of the top layer lies on top of the A sublattice of the bottom layer. Likewise, there are the BA sites and the AB sites that also form triangular lattices. But the way to understand this model quantitatively is to go to momentum space and to use the fact that the low energy behavior of the graphene Dirac cone, the graphene in each layer is that of graphene Dirac cones at the corners of the Brouwen zone. So in particular, we have two inequivalent graphene valleys, the K valley and the K prime valley. Here I've shown the Brouwen zones on top of each other and rotated by the twist angle. And so let's focus on the K valley. The K prime valley is related by time reversal symmetry. If we look at the Hamiltonian for the K valley, we have the Dirac dispersion for each layer, as well as tunneling between the layers. The tunneling has a piece that takes the same sublattice to the same sublattice, as well as opposite sublattices to each other. So like AA, BB, BA, AB. And the functions U of R here contain terms that boost the momentum of the graphene cone in one layer to the graphene cone of the other layer. So these Q's are precisely the momentum that connects the graphene Dirac cones in each layer. And the band structure is highly angle dependent, but at a magic angle of around 1.1 degrees, we get two extremely flat bands around zero energy. And this is, remember, per spin per valley. So we have a total of 8 flat bands. And so we can have a filling nu that goes between -4 and 4. And charge neutrality is at nu equals 0. I also want to point out that there's an important parameter inside this model, a dimensionless parameter, that's the ratio of this AA to AB hopping, W0 over W1, which we would call kappa. And nominally, this value is 1 if the structure is pristine and unrelaxed, but both lattice relaxation of the actual crystal, as well as the renormalization group, results in an effective kappa that's less than 1 for the low energy behavior of the system. And it's the method you choose for the lattice relaxation, as well as your cutoff for the normalization group, both contribute to some uncertainty in what that value of kappa is. And a conservative range for the values of kappa could be anywhere from 0.5 to 0.8. And we'll see that this parameter is actually very important. And so the physics we can expect to see can depend very strongly on what the realistic value of kappa is. So I want to introduce churn bands into the system. And I want to motivate that introduction by one piece of the correlated physics that twisted bilayer graphene hosts. That piece is that it hosts the anomalous Hall effect when it's aligned with a hexagonal boron nitride substrate. So when we align TBG with a HBN substrate, the main effect of that is to introduce a sublattice potential. If we introduce a sublattice potential for an ordinary graphene, we don't get churn bands because the graphene Dirac cones in each valley have opposite chirality. But in twisted bilayer graphene, because the Dirac cones in a single valley come from the Dirac cones in a single valley of graphene, of both graphene layers, the Dirac cones in this band structure here at the Km and Km prime point actually have the same chirality. And so when we introduce a sublattice potential, they split apart in energy and the resulting bands have churn number, unlike in graphene. And as a result, we can imagine a correlated state where working at nu equals 3, we fill up every churn band except for 1. And that will make the system have a net churn number and display an anomalous Hall effect. And this is what Andrea Young's group found in this paper here. And there were previous experiments done in the Caltech group by David Goldhaber Gordon, but I'm showing this one especially because it shows a very nice hysteresis that underscores that time reversal symmetry is broken, where we picked one churn band to be unfilled, as well as the fact that it gets a quantized value of the Hall conductance, showing that really you do get these churn bands isolated from each other.
I have some questions.
Yeah.
So first of all, when you say sublattice symmetry breaking, is that like AB to BA or AB sublattice symmetry breaking? You mean AB to BA?
I think I don't mean, I don't think there's a, I didn't mean to say that there was a symmetry.
The sublattice delta sigma Z, what is the sigma space? Is sigma space?
Oh, it's the AB of the graphene.
Of the monolayer, AB
Yeah.
of monolayer graphene. Okay.
Yeah.
Okay. And next question is, I don't remember the details. Is there, so you know, in the purest sense of anomalous Hall effect, we should have it as, you know, zero field. Do they see this as zero magnetic field? I guess hysteresis is as a function of magnetic field.
At zero field, they have a quantized value.
Okay.
Yeah. But they see hysteresis when they introduce a field because
right.
Yeah.
All right.
Okay, thank you. Right, so I want to talk about a different way to see the emergence of these churn bands, because it'll connect to what I talk about for the rest of my talk, and I'll also get to introduce a very interesting model that's been used all over the twisted Bayesian graphing literature at this point. And we can kind of regard this as a strong coupling origin of the churn bands, which I think is favorable for thinking about the energetics, because the Dirac points of a flat band aren't so crucial to the energetics, because once you start, like, the bands are very, very flat. So I want to talk about a strong coupling origin by this chiral model. So the chiral model begins with the approximation that we neglect this AA and BB tunneling terms. So we only have tunneling terms between opposite sublattices. This is what gives the chirality of the model, because now the Hamiltonian anti-commutes with this sublattice operator sigma Z. As a result, the zero energy states can actually be labeled by their sigma Z eigenvalue. So if H psi equals 0, then we can label psi with a sigma Z eigenvalue. And also H takes this form with D in the bottom left and D dagger in the top right, because it's off diagonal in sublattice. And an important thing to note about this D operator is that it only depends on anti-holomorphic derivatives. And this is actually very similar to the problem of the quantum Hall effect in graphene. So I'm going to spell out that analogy quickly now. In the quantum Hall effect in graphene, we have the Hamiltonian is sigma dot P minus EA. And this can also be written with the D in the bottom left and the D in the top right, D dagger in the top right, where D also only contains anti-holomorphic derivatives. There, the zero modes of D form the zeroth Landau level, which is an exactly flat band at zero energy. Now, there's no guarantee that the chiral model has an exactly flat band at any magic angle, because this operator has to host an entire flat band of zero modes. But it turns out at the magic angles, this actually does happen, and we get an entire flat band for both sublattice A and sublattice B. So the way to see that is we can actually build the entire band of zero modes starting from a single one, psi k of r. The way to do this is to note that because D only has anti-holomorphic derivatives, we can write D acting on f of z psi k is equal to 0 because f of z is chosen to be a holomorphic function, and so it passes right through D. However, we can't do this at every angle because f of z as a holomorphic function, it either has to be constant or it has to blow up somewhere by Liouville's theorem. And so this wave function here is usually not normalizable. However, there's a rescue at the magic angles because it turns out at these points, at these points, there's the psi k of r at a specific point r0 has a 0 in both of its components. And that means we can put the poles of this holomorphic function f of z at the same place as this psi k has its zeros. And so we can construct a function that looks roughly like this. There are several ways to write it. But the point is that there's a theta function in the denominator here, and this theta function has zeros when z is equal to z0, which is the complex coordinate that corresponds to r0. And as a result, this entire fraction here, despite the poles in the denominator, is normalizable. And then we multiply by some holomorphic function fk of z to get and we choose fk of z carefully to get the block periodicity right. And by choosing various fk of z, we can build the entire band of zero modes in a unique way.
How do we understand psi k of r naught is exactly 0 at magic angle?
Right. There are, so in the original paper that introduced this chiral model by Grisha and Ashwin and Alex, they showed that if the Fermi velocity vanishes, then this is guaranteed to be true. But as of now, there's no way to start with the Hamiltonian and predict where exactly either the
Fermi velocity is going to vanish.
Yeah.
Okay.
The reason for formulating in terms of the Fermi velocity is it's a single real parameter in your tuning. So it seems less unbelievable that this that this would happen. So it's a little more believable that the Fermi velocity would have accidental zeros, but I think there's still a lot of mysteries about where these angles occur. And so I think that's still an open problem.
I see. But the point is that there are these angles where Fermi velocity vanishes was something McDonald and Bistritzer discovered. But in this first paper of the chiral model, the authors realized you can get a lot of juice out of it.
Yeah.
More than just band is flat. Like you can get a lot of handle using this model.
Yeah, and that's what I want to talk about for the rest of the talk is really dive into these wave functions and what makes them special. But the problem of actually figuring out where these magic angles are analytically is unsolved. In particular, there's a quasi-periodicity to the angles, and that doesn't have an analytic explanation.
So another quick question. So in this chiral limit, can you say something about the higher dispersive bands? Like, can you extract some general lessons about those? Is there some interesting structure that shows up with those as well?
That's a good question. I'm not familiar with anything because I think the main power that the chiral model gives you is that because of this property that the zero modes of sublattice polarized, it lets you to divide the problem in half, and the zero modes are guaranteed to have an interesting structure because of the zero modes of this anti-holomorphic derivative. I'm not sure if there's anything nice that can be said about the higher bands because that property doesn't hold there. But on the other hand, it's a special model and some special things might happen. One thing that's important for practical considerations is that the band gap to the remote bands is actually a lot larger in the chiral limit.
So if you were to include perturbative corrections in W0 over W1, the actual band gap reduces?
Yeah, the gap to these remote bands will reduce.
Ah,
We'll see some effects of that in actually the band geometry of the bands here. Later on, we'll see that the Berry curvature changes as the band gap gets smaller.
so actually, I'm vaguely remembering a figure from Ashwin and Grisha's original paper, and correct me if I'm wrong, but I thought they started getting in this chiral limit some of these higher dispersive bands also as flat. Maybe Aslam
Oh
knows
yeah,
this.
I don't think that's definitely
I-
true.
Is that
I don't think
generic
those
or
are
is
well
that
understood.
okay?
Maybe Islam, are those well, have you understood those? If anyone has, I think Islam might have.
Yeah, I don't think, and well, the bands kind of get a bit flatter, particularly at higher magic angles, but I don't think there is any like. I think there is a general, when you look at higher magic angles in particular, like ones below the first magic angle, there is a general exponential squishing of the bands. I think that there were recently some mathematics papers that studied this model and it discussed this exponential squishing of the bands at very small angles. So that's the only analytical work that I know that discusses the flatness of the other bands.
Right.
Yeah, the
And-
exponential squishing is definitely there. It makes the model very hard to solve at large alpha.
Yeah,
yeah, may I ask just a quick follow-up? As in those higher bands, I guess they're not really flat, right? I mean, it's just very non-dispersive. But those higher ones that they are just looking like flat, but they're not exactly flat. Did I get it right? Or it's unknown?
I think I vaguely remember that there were some that looked very flat at special points, but I don't remember. I'll need to check again.
Because I myself encountered cases where I thought I got a perfect flat band, but if I zoom in enough, I see a
I see.
10 to the -6 dispersion of some kind. So it's kind of annoying. Oh, I mean, right? This is okay. It could happen. I'm just saying. Yeah.
I think at the first magic angle, all the higher bands are very dispersive.
Yeah, definitely for the first magic angle.
Like
What
at
of
the
the-
third,
You're saying beyond the zero energy band, everything is dispersive,
yes.
but some of them may have less
But-
dispersive than others. Okay.
But yeah, I think the third magic angle, for example, there are some of the remote bands look flat. And yeah, I don't know if someone has looked deeply into this and maybe there's something there. But yeah, actually a small comment I wanted to say also is about this psi-k of R of 0. I just wanted to say that this R of 0 is a special, is usually a point of a special symmetry. So one of the two components always vanishes by symmetry.
Yeah,
So
the
the
bottom
condition-
component here always vanishes.
So the condition is not as, like, it's not tuning two parameters to hit 0. It's just tuning one. Like you need one real number to hit 0.
Yeah. Right. So yeah, thanks everyone. I think it's good to put this model in context, and I think there's a lot of interesting work to be done on it still. But yeah, before I move on, the last thing I want to point out on this slide is that we have two bands of opposite sublattice, and when we add an HBN substrate, they split apart in energy completely uniformly because they're completely sublattice polarized. So this gap here is exactly 2 delta. Also on symmetry grounds, we can relate the wave functions of these bands by C2T symmetry, which acts within a single graphene valley. And of course, C2T is broken by this sublattice potential because C2 is broken, and so that's why we get the splitting. So this lets us kind of provide a bird's eye view for all of twisted bilayer graphene in this ideal limit. We can think of there being 4 churn +1 bands and 4 churn -1 bands. So recall in the previous slide, we found 1 churn +1 and 1 churn -1, but we were working with a single spin and a single valley. So when we vary over all the spins and all the valleys, we quadruple this. And furthermore, all these, in the chiral limit, all the churn +1 bands are related by symmetry. And so there's a U4 symmetry that rotates the churn +1 bands and a U4 symmetry that rotates the churn -1 bands. And so in total, there's a U4 times U4 symmetry in this chiral limit where we don't have any dispersion. If we do have dispersion that couples these, the two churn sectors, and that reduces symmetry. Also, if we move away from the chiral limit, these bands aren't exactly the same anymore, and that also reduces symmetry. But we can consider this as like an unperturbed, highly symmetric model, and then regard dispersion and outside the chiral limit as perturbations. And this is really the basis for a strong coupling theory of twisted bilayer graphene, where we can understand a lot about the insulators as well as the potential for skyrmion superconductivity in the system using this starting point. And I want to highlight here, me, Islam, and Ashwin put out a pedagogical review of this strong coupling theory, where we start from really the BM model and build all of it from scratch. And we hope this will be helpful for people who are interested in working with this way of looking at twisted bilayer graphene.
I have a question.
Yeah.
The quantum integer quantum Hall, where you have churn number 1, you can understand that time reversal symmetry breaking from like bulk versus edge picture, and you can also understand it from the the orbitals picture, right? That orbital picture gives you a very kind of real space picture. Both are kind of real space picture, right? When you say there is an edge current, C = 1 edge mode, or when you say you have the circulating loops and nobody's going anywhere, but you just have this skipping orbit at the edge. So that skipping orbit is a very microscopic, I mean, it's kind of a microscopic real space picture, and all of it is a very real space picture. Can we form sort of a analog of that for this setting of, what does chiral model mean? Or is chiral model just taking one of the C's, C = 1 versus C = -1? You're actually taking 0 delta and opening up the gap, right? So can one form that kind of analogous picture with like integer quantum Hall?
Right. So I think the question of, I think to me, it seems like there are 2 questions there, one of which is how do we understand the circulating picture in a general churn band? I think I'm not sure of a fully satisfactory point of view, but I think one thing that you can maybe say is that one thing in the lowest Landau level is that the projected position operators don't commute. And we can kind of think of that as encoding the fact that there's some uncertainty in the position because of the circulating currents. And that upholds in a churn band as well. The commutator of the position operators is given by is related to the Berry curvature.
So you're saying there is something like the magnetic algebra here?
Yeah, though it's it's a little subtle. Like the GMP algebra for the densities doesn't hold in generic churn bands, for example. So there are special aspects to the lowest Landau level that, I mean, one way to think about it is the fact that these orbits are perfect circles is not going to hold in a general churn band because we don't have rotational symmetry, and the orbits will the shape of the orbits will also depend on which point in k-space you're effectively at, or how you build the orbital in k-space. So it's a little complicated, but I think qualitatively it still has some of those pictures. Maybe you can also view it from adiabatic continuity. One of the things I'll show later is in we can actually, we can show that chiral twisted bilayer is adiabatically continued to the lowest Landau level in a natural way.
Mhm.
But maybe another thing that I'm not sure if this was what you're asking, but how do we see these churn bands when we move away from the chiral model? Is that,
Mhm.
yeah. So,
Yeah, maybe, yeah. Mhm.
so we can understand that as follows. So it's in the chiral model, it was very nice because the churn bands are sublattice polarized. So we just restrict to a certain sublattice and we get a churn band. For
Mhm.
the realistic model, we don't have perfect sublattice polarization, but we can still diagonalize the sublattice operator. So we choose a basis where UA, like gamma AB is UA, sigma Z, UB is diagonal. So we're just taking the two flat bands together and just choosing a basis for them, one in which the dispersion is not generically diagonal. But this basis where we diagonalize the sublattice operator is adiabatically continued to the sublattice polarized chiral churn bands.
And the sublattice polarization is again the graphene AB sublattice, right? The monolayer
Yes,
sublattice.
yes.
So that's a very small scale
Yeah,
from the
it
like Moray scale point of view.
It really is. It's
Yeah,
it's not very intuitive, but maybe another analog
it's
is,
very, very not intuitive.
yeah. So I think, yeah, I actually had the same question when I first started working on twisted bilayer graphene, and I
And
asked
did you
Austin
find
that.
the resolution to that question?
I think I did
Came
in
to
the
peace
end.
with it?
Yeah, I think I made my peace with it. But the
Uh-huh.
answer Ashwin gave me was that
Mm.
the lowest, if you think about the lowest Landau level in graphene, that zero mode is also sublattice polarized, even though the magnetic length can be way bigger than the graphene lattice scale.
Yeah. All right.
Mhm.
That's something. Yeah.
Yeah.
But but is your magnetic length scale? I guess magnetic length for you, I mean, you're like the Moray lattice constant is kind of like your cutoff, right?
Yeah, so in a precise sense, and this will be actually very precise later, we should regard 2 pi times the magnetic length squared is the Moray area.
Okay.
Yeah, 1 flux quantum per Moray area. Yeah, I also want to point out that this picture for churn bands actually has a direct experimental relevance because in this group by this paper by Das and collaborators in Nature had this showed that when you introduce a perpendicular magnetic field in twisted bilayer graphene, you can get churn insulators appearing at very small fields and at relatively high temperatures. These have a very simple interpretation in terms of filling these churn bands. So at charge neutrality, you fill 4 churn plus bands and you get this churn 4 state. At filling 1, you add in a churn -1 band and get churn 3 and so on. Yeah, I think this basis is very real and worth thinking about for a lot of TBG problems. But moving forward, I want to make a really critical comparison between these churn bands and the lowest Landau level, and try to come up with some good geometrical indicators that tell us that give us hints as to what physics these churn bands can host. So to do that, I want to make precise what makes the lowest Landau level special. And a key aspect of this is that when at least I thought about the lowest Landau level before getting into this problem, I was like, okay, it's has flat Berry curvature and it's a flat band. If you can reproduce that, then you probably reproduce much of the lowest Landau level. But higher Landau levels have both of these properties, and they have very, very different physics. So if you're, and in particular, there's for at least above the, let's say the third Landau level, there's no fractional quantum Hall effect. And instead we get charge density waves. So somehow we want a description of flat churn bands that can encode this and is generalizable to arbitrary churn bands, not just Landau levels. To do this, it's worth considering the wave function overlaps between a wave function at the periodic wave function at k and the wave function at k plus q. The reason this is a nice object is that it sums over all the orbital indices with this inner product. And so you can compare different churn bands to each other, even though the orbital spaces might be different. The phase of these overlaps is captured well by the Berry curvature because this encodes precisely the gauge invariant part of this phase. However, the magnitude is in principle independent, somewhat independent of the Berry curvature. And to talk about the magnitude, we can define a distance function between 2 points in k-space as 1 minus the absolute value of the overlap. And then from this distance function, we can define a metric called the Fubini-Studi metric, which we get by differentiating this distance function in the usual way. And this metric, I'm going to argue, is very important because it precisely encodes the difference between the various Landau levels. So this n is the Landau level index, and this metric linearly increases essentially with the Landau level index. And so it differentiates all the different Landau levels from each other. And furthermore, this n actually comes from a very important part of higher Landau level physics. If we consider the overlap, also sometimes called a form factor, then this is proportional to a Laguerre polynomial. And this Laguerre polynomial with index n is present only in higher Landau levels and is actually directly responsible for the reason we see charge density waves in higher Landau levels, because the zero of this Laguerre polynomial gives a favorable cue to host charge density waves at. And additionally, this Laguerre polynomial is directly responsible for this n in the Fubini-Studi metric.
May I ask something real quick? Sorry. Yeah. I think maybe if you'll get to that at a later point, I'm happy to wait. But it just seems like if I'm staring at a fixed n, I could totally redefine LB to absorb everything into that. So
that changes the Berry curvature though, as well.
Well, if I just measure the Berry curvature in terms of, let's say I always rescale my Booleanzone so that it's going from 2 pi to 2 pi in both direction, then then I'm always having uniform Berry curvature, and then in that sense, nothing is different, right? So
I think you're hitting on an important point, is that we should really compare the scale of this metric to the scale of the Berry curvature.
The scale of Berry curvature. Okay.
So in particular for the lowest Landau level, and I'm going to get to this in the next slide, what's true is that the Fubini-Studi metric is equal to 1/2 times the Berry curvature. And if we scale LB, then both the Berry curvature and the Fubini-Studi metric scale in the same way.
Mm-hmm.
And this condition is invariant of any coordinate choice you can't just scale things to remove this condition.
Okay, maybe, yeah, but I guess maybe ultimately I'm just kind of confused about this statement that I think I can totally write down some valid fractional quantum Hall state residing in the third Landau level. Mm-hmm. Possibly even finding an exact Hamiltonian for that, but you're probably implying that that's not a natural thing to do in some sense. Is that what you're trying to say?
Yeah, I think you can do that, and I think you can probably write down a probably somewhat weird Hamiltonian that would give that as a ground state. Right. But what I'm going to argue is that this directly translates to being a ground state of a Laughlin state in a short range potential.
Okay. So I guess maybe at some point you would make some assumption about what's natural, what's not, right? 'Cause otherwise,
Yeah.
right? Okay.
Yeah.
Right.
No, I agree. In principle, you can create fractional quantum Hall states in any churn band just by mapping the Hilbert spaces.
Exactly.
So we have to introduce some naturalness or energetic constraints to really think about this. You can't solve this problem entirely from geometry. But it turns out that, at least in the case of the Laughlin states, this geometry is very intimately connected to short range interaction potentials.
I see. Thank you.
So that's what I want to argue here is that
I have a question. I have
Yeah.
a question. So the arguments that you've given is going to be, it's essentially, doesn't it boil down to harmonic oscillator ground state is exponential and Gaussian, and everything else has a polynomial multiplied to it. It's got longer tail. So, you know, you look at interactions, is also, if you project to that wave, that state, there's a longer range component.
Yeah.
Um,
For the Landau
and
levels, I
it's
agree.
that's
the best way
not
to look at it.
going to give you a specific threshold. It's just things are going to become more and more different
Mhm.
from lowest to the next to the next to the next, right?
Yeah.
So I'm okay. So is your metric going to play an action? I mean, if I want to look for something that depends on n, the energy levels is n+1/2 h bar omega c. I knew that since, I don't know, whenever I first learned quantum mechanics, so it didn't take inventing a metric to see something that depends on n.
Mhm.
Is your metric going to play an important role on something that you're going to discuss? Or was it
Right.
your way of looking at something that depends on n? Because
So
I
I
had
think-
an easier thing that depends on n.
Yeah, so I think if we're only looking at Landau levels, then the metric is kind of a silly way to think about it. It's way overkill. But if we're looking with the generic churn band, which has a lot less symmetry than Landau levels and doesn't have a harmonic oscillator description, and in particular doesn't even have the analog of higher Landau levels often, it just has a churn band.
I see. So you want to
then-
consider a situation, somebody gave you a churn band and you just know the churn number. What can you say about it? Is that sort of
Yeah,
what you want to consider?
if you have the wave functions and you know the churn number, what can you do? And
Okay.
one thing you could do is form this metric and then compare this metric to various Landau levels and see, is it going to display lowest Landau level physics, first Landau level physics? Who knows? So I think this technology, was really developed for the problem of fractional churn insulators, where people are trying to replicate the quantum Hall effect in churn bands where you don't have this nice Landau level description where everything's much more transparent.
So just a very quick question, maybe you're going to get to it. So the metric is always bounded from below by the Berry curvature.
Yes, that's exactly what I'm about to say, yeah.
Okay, and you're going to tell us something about how that somehow plays into this. And
Yes.
Okay, then I'll wait.
Yeah. Right. So the way to see this bound that was just alluded to is it's useful to combine the metric and the Berry curvature into this object, which we can call the quantum metric eta. And eta is gauge invariant, as can be explicitly checked. And it can be thought of as a projection of this matrix Q onto the states spanned by the partial derivatives of these states up to a normalization. And Q itself is also a projector onto the orthogonal subspace of U. So in particular, what I want to emphasize is Q is positive semi-definite. And since eta can be regarded as a projection of Q, eta is also positive semi-definite. And it's also gauge invariant, as we would hope. And that implies the inequalities that were just alluded to. In particular, we know that the determinant of eta is greater than equal to 0 because it's positive semi-definite. And that directly implies plugging this formula in for eta, that the determinant of the metric is greater than 1/4 of the Berry curvature squared. And also that the trace, using the inequality that the determinant is greater than just a 2x2 matrix inequality, we can get to this inequality where the trace of the metric is greater than or equal to the absolute value of the Berry curvature. So this is the inequality that I want to emphasize. And the way the specialness of holomorphic wave functions in the lambda level comes in is we want to, whenever we have an inequality, it's useful to think about what systems saturate that inequality. So for example, harmonic oscillators we know are special and they saturate Heisenberg's uncertainty principle. It's useful to think about what systems can satisfy this inequality here. And the answer is that this turns out to be a very special inequality, and the saturation of it is referred to as the trace condition in the literature. If we also, on top of the saturation of this inequality, demand that the Berry curvature is homogeneous, then in many ways, people have showed that you can exactly reproduce lowest Landau level physics. One sense in which that's true is you can derive the GMP algebra holds. And this algebra really is what you need, because if you have your Hamiltonian that in terms of the density operators and you have the algebra of density operators, then you've essentially recreated the interacting physics of the lowest Landau level. So what I want to argue is that when this condition is saturated, you've gone a long way towards recreating the physics of the lowest Landau level. And what we showed is that chiral twisted bilayer graphene exactly saturates this condition. Trace of G is exactly equal to the absolute value of omega.
Sorry, just one more question. So I don't know if this is relevant to your discussion, but so I remember that Sid Parmeswaran and Shivaji Sondhi and others many years ago were taking some long wavelength limit of the Chern band and trying to connect it to the GMP algebra. And then you get corrections beyond this term that you've written on the right-hand side. Are those corrections somehow controlled by this metric or some different?
This is actually the full GMP algebra with no corrections.
Right.
The result by Sid and Sondhi is that you take the linear, or you expand the sign to linear order. And then you get this full, if you try to match the corrections, then you end up rederiving these conditions, wanting to saturate these conditions, and then you get the full algebra.
I see. Okay.
Yeah, this is what Roy did. He looked at the higher order terms and expanding the sign and derived that these conditions were important, and then found the GMP algebra.
Okay.
Yeah, it's in this paper that I first put right here.
We have some young graduate students in the audience. Can you spell out what GMP is?
Right.
And what's underlying this statement about GMP algebra?
Right. So the GMP algebra is named after Girvan, McDonald, and Plotzman in a paper that they had in the 90s. And what they did is they used the high magnetic translation symmetry of the lowest Landau level to derive that the commutator of the density operator projected to the lowest Landau level obeys this algebra here. And there are various nice mathematical properties of this algebra, but one thing that they used it to derive is that is the excitation spectrum of neutral modes in the lowest Landau level. So things called the magnetoroton mode. But more recently, this algebra has gotten more attention because there's been more interest in understanding how to understand the lowest Landau level if you begin in the lowest Landau level and end in the lowest Landau level. It's like writing chiral wave functions is really working in the enlarged Hilbert space of free particles. But can you start with the problem projected to the lowest Landau level and derive the fractional quantum Hall effect? This algebra is very important towards those efforts.
But the algebra itself is a statement about the Landau level, which is kinetic energy only, right? You get the Landau level by putting free electron under a magnetic field.
Yeah.
So there is no interaction is not involved in it. You're deriving it based on the wave functions of the quantum mechanics problem.
Right. So The algebra doesn't involve the interaction at all, but the Hamiltonian.
Right.
So the Hamiltonian will be like H is some over Q, some V tilde, which is slightly different than the.
So the
normal-
assumption is you have this algebra, which is a statement about your non-interacting physics under a magnetic field
Mhm.
and your exact eigenstates of the non-interacting physics. And then you say, well, my interaction is going to be written in terms of the density operators.
Mhm.
And if that same density operator satisfies this algebra, then when you put that into your Hamiltonian, you have to, that there's going to be specific consequences associated with that.
That's the idea.
Mhm.
Exactly.
But that sounds like it's trying to take interaction sort of perturbatively. Because your starting point is non-interacting physics.
Well, it's taking interactions perturbative compared to the gap between Landau levels.
Mhm.
But
Yeah.
within the Landau level, the
Mhm.
interactions
Yeah.
are on the scale.
Right. Yeah.
So in
Within
that
the
sense, it
Landau
is
level there.
perturbative, but
Mhm.
it's
Okay.
even within the perturbation theory that the interaction is smaller than h bar omega c, it's still a very hard non-perturbative problem.
Mhm. Yeah. All right.
Right. So yeah, let me quickly talk about why chiral twisted bilayer graphene exactly saturates this condition. It essentially has to do with holomorphicity. So this D operator only depends on anti-holomorphic derivatives. Recall that D acts on the wave function psi to give 0, but we're interested in the wave function, the periodic wave function U, which is e to the minus I k r psi. So for U, we're interested in the operator D conjugated by e to the ikr. And what this does is it shifts the anti-holomorphic derivative by kx plus iky. So in particular, this k-dependent D only depends on holomorphically on kx plus iky. As a result, because the zero mode operator only depends on kx plus iky, we can choose a gauge where the periodic wave function also only depends on kx plus iky. This doesn't always have to be true. We can choose a gauge where this isn't the case, but we can also always choose a gauge where this is the case because the zero mode operator only depends on kx plus iky. If we choose this gauge, it's very straightforward to evaluate the structure of eta because when you act on U with, say, an x derivative, sorry. When we act on U with an x derivative, we can replace partial x with a holomorphic derivative and partial y with I times a holomorphic derivative because the anti-holomorphic derivatives vanish. As a result, we get this structure for eta, and that based on this equation here, that implies that the Fubini-Studi metric is tied to the Berry curvature in this way, and the trace condition is exactly saturated.
And is it easy to see already at this level? If I turn on an infinitesimal W naught, what are the corrections to the metric because of that?
Right. So the infinitesimal W, the W naught, will cause mixing with the remote bands, and that'll eventually cause the metric to this condition to not be true. I'm going to talk about what happens.
Okay, sorry.
Yeah, I'm going to show plots of these conditions as we increase W naught. So with this, it seems like chiral twisted bilayer graphene is very similar to the lowest Landau level, and we can actually make this analogy transparent in the real space wave functions as well. Recall that the wave functions of chiral twisted bilayer graphene were holomorphic in real space as well, so this may not be that much of a surprise. But to precisely carry it out, we have to do a slight generalization. We have to consider the lowest Landau level in an inhomogeneous magnetic field for Dirac electrons. So this is a setup where the magnetic field is inhomogeneous. It's solved in the standard way by starting with the sublattice polarized ansatz and then solving the zero mode equation here. And the result is slightly gauge dependent, but it takes the general form shown here, where this e to the minus k of r is like the analog of the usual factor. E to the minus k0 is e to the minus like y squared over 2lb squared in the Landau gauge. This is just a generalization of this solution to inhomogeneous magnetic field. And turns out you have to solve this equation and be compatible with the gauge you chose for A. So the statement is that if you choose your magnetic field correctly, we have exactly that the twisted bilayer graphene wave functions are the lowest Landau level wave functions, together with a spinner in layer space. So this layer space spinner had to be there because chiral twisted bilayer graphene has a layer index and the lowest Landau level doesn't. But the important piece of it is that it's the same for all the states in the band. It doesn't depend on K at all. And so in any overlap, like UK plus Q, this spinner goes away. And so in terms of band geometry, the two systems of chiral twisted bilayer graphene and the lowest Landau level in this magnetic field shown here are exactly the same.
Why did the magnetic field had to be heterogeneous?
Right.
Is it like the Murray potential? I mean,
Yeah.
periodicity?
Yeah, it has
Or-
the same periodicity as the Morey pattern, exactly.
Mhm.
So the lowest Landau level in a perfectly homogeneous magnetic field has perfectly homogeneous Berry curvature because of magnetic translation symmetry.
Mhm.
Chiral twisted bilayer graphene doesn't have magnetic translation symmetry. And so the Berry curvature in chiral twisted bilayer graphene is actually weakly inhomogeneous. It's actually very close to homogeneous, even though it didn't really have to be. But it is slightly inhomogeneous. And as a result, it can't be related to the homogeneous field, lowest Landau level. And so it turns out to be related to an inhomogeneous field one.
Actually, here I have a question. So I understand that let's look at the first half of the page where you introduce the relation between K and B. If B is all positive in space, or let's say it integrates to some finite value,
Yeah,
with a fixed sign, then K just definitely grows. So that guarantees the normalizability of psi LLL.
right.
But when we map it to this picture that you drew, definitely there are some parts that is negative, some parts that are positive. So are you saying that there's a net B if I integrate over a large region, or is
Yeah, this has the net, if you integrate over a unit cell, it's one flux quantum.
sorry?
If you integrate over a unit cell, it's exactly one flux quantum.
Oh, I see. I see.
Yeah.
I see.
Yeah, you can decompose it into a constant piece and an oscillating piece.
I see. Okay. Right. Well, so long as you have a constant piece, at least the normalizability is guaranteed.
Yeah, exactly. So this is what we found in our work for the case of chiral twisted bilayer graphene. But I want to also mention this work by Jie Wang and her collaborators, which showed that if for Chern number 1 models that are defined in continuum space, this is actually always true if the trace condition is saturated. So if you saturate this trace condition, which is a momentum space band geometry condition, you can actually work out that the wave functions are related to lowest Landau level ones exactly in this way. So this is essentially always true for these ideal Chern 1 models.
So have you thought about does this effective magnetic field have a meaning? Like, can it help me think in sort of real space basis? Because if I want to think about interaction, yes, you can think in terms of your density operators and stay in the K space. But so your field is,
I think this is my next
don't-
slide, actually.
okay, all right.
So in fact, we can make the same arguments for the fractional quantum Hall effect in real space for chiral twisted bilayer graphene as for the lowest lambda level. So the statement is that for both the lowest lambda level and chiral twisted bilayer graphene, the many body states are proportional to a holomorphic function of n complex variables, because the single particle wave functions are labeled by holomorphic wave, are proportional and labeled by holomorphic wave functions. So the idea is to choose this f of n complex variables so that it pays no energy to sufficiently short range potentials. What's done in the quantum Hall effect pioneered by Haldane is you can write down pseudo potentials, which are good approximations to very short range potentials. Written in real space, these take the form of a series of derivatives on delta functions. So the zero pseudo potential is just a delta function. The V1 is a Laplacian of a delta function. So let's say we truncate at exactly this order. Then in that case, we can show that the Laughlin state at filling 1/3, where the particles vanish as the cube of the distance as two particles approach each other, actually pays no energy to this pseudo potential. And we can construct this explicitly using chiral twisted bilayer graphene wave functions or lowest lambda level wave functions in any inhomogeneous magnetic field. And so we found a ground state in these ideal potentials. And just like the lowest lambda level, we hope that as you tune to more long range potentials, these remain ground states as well. I want to emphasize that this is really the same argument that's done in the lowest lambda level for the stability of the Laughlin state, because the usual argument is done in terms of rotation symmetry, where you use symmetric gauge states and diagonalize the interaction in terms of them. But the symmetric gauge states really just, symmetric gauge states really just label how fast the wave function goes to 0 when two particles approach each other. And so the argument turns out to be exactly the same. So we can do this argument without rotation symmetry using the zero clustering argument. And this argument was actually made in the quantum Hall effect literature as well to argue that the Laughlin states weren't sensitive to rotation symmetry. So with all this said, I think we can be very optimistic that the chiral model can host fractional Chern and Slater states. But for the realistic model, it's much less clear. And that's because the band geometry gets much less like the lowest lambda level as the W0 over W1 kappa increases. You can see that through two indicators, the inhomogeneity of the Berry curvature and the violation of the trace condition, how much the violation of the trace condition. So the Berry curvature really spikes up as we increase from kappa equals 0 to kappa is 0.8. And that's really because the remote bands come closer to the active bands. And so I've plotted the various indicators here, the mean square inhomogeneity of the Berry curvature, as well as the violation of the trace condition. And we can see that they increase very sharply as kappa increases. And as a result, the physics we can expect is highly kappa dependent. So maybe if kappa is 0.5, we can be optimistic. If it's 0.8, maybe not so much. But nonetheless, people actually see fractional Chern and Slater states in exact diagonalization for realistic values of kappa around 0.7. And this came out around the same time as our work, and we were really excited to see that the numerics showed that what we showed doesn't immediately die out as soon as we go to the realistic model. So in particular, I've attached a plot from this last group here that shows the three degenerate Laughlin ground states. They're split by finite size effects. and they flow into each other under inserting a flux quantum through one of the torus handles. And this is a really smoking gun signature that there's a fractional quantum Hall state in the numerics.
How does the how would the real interaction potential compare to, you know, like you're studying pseudo potentials, right? And pseudo potentials give Lofting state as an exact solution.
Mhm.
But for the magic angle bilayer graphene, you know, if you take not only this kappa issue, which is about the band structure, but you know, given the low density system, interaction is not as screened and and things like that. How would that affect? Like, would we see this in experiment? And if we were to see this in experiment, where should we have already seen it?
Right. So, sorry. This, yeah, I think this is a question that only exact diagonalization and DMRG studies can really answer. I think our goal was to show a beautiful chiral model that shows that fractional translator states are especially ideal there. But ultimately, we did make uncontrolled approximations. And so that's why I think these exact diagonalization studies are very important to show that the physics at kappa equals 0 can continue up to realistic values with realistic interaction potentials as well. So these studies didn't use pseudo potentials.
But they are not working with you know, so many atoms inside the unit cell either, right? So they are working on some triangular lattice Hamiltonian.
no,
What is the Hamiltonian they studied?
So I think at least some of them work with the full BN Hamiltonian.
BN Hamiltonian. Okay. Yeah. Okay.
So some of them, I think the worst part about some of them is that they don't take a realistic dispersion. We know the band geometry is important, but ultimately, if the dispersion is large enough, then the system is just going to want to be a metal. And so I think some of them do not use the physical, like Hartree-Fock corrected dispersion from integrating out remote bands. So we know that remote bands increase the dispersion of the flat bands a lot through Fock corrections. And I think only this first study incorporated that. But they still found an FCI, but only in certain parameter regimes.
Are they using Coulomb interaction? What are they using for interaction if they're using BN
Coulomb.
model, which is low
Coulomb
energy
screening.
effective theory? Coulomb.
With screening, but we expect there
Coulomb
to be
is screening.
Yeah. So this first study found that at larger angles, there was an FCI ground state, essentially. They actually tuned W1 instead of the angle. But at smaller angles, the Berry curvature is more inhomogeneous. And to get an fractional translator state there, you need to use probably unphysically short screening length.
So now if I take a bold step of trying to see this in real experiment, what density should I have seen incompressible state?
Right. So I think the natural starting point is to work near fillings where people have observed integer quantum Hall effect at 0 filling. So sorry, integer quantum Hall effect at an integer filling. So I think a natural starting point is starting with nu equals 3 and then doping the system.
Okay.
And so I'm optimistic that future experiments at nu equals 1/3 and nu equals 2/3 might show it. I think it's going to be very parameter dependent because this Berry curvature does get very, very high, and the exact diagonalization studies show that it's very touch and go whether you get an FCI or not. So you probably need a very clean system in a very favorable parameter regime.
All right.
So this is my concluding slide. I just want to kind of summarize the various results I showed in this talk and kind of provided in a unified picture. Both chiral twisted bilayer graphene and Dirac lowest lambda level have a zero mode operator that depends on anti-holomorphic derivatives. In real space, this tells us that the trial wave functions are labeled by holomorphic wave functions. And in K-space, this shows that the trace condition is exactly saturated. And additionally, if the Berry curvature is homogeneous or the magnetic field is homogeneous, then you get the full GMP algebra of the constant field lowest lambda level. And again, I want to mention that the work by Jie Wang et al. Showed that you can go directly in between the trace condition and the fractional quantum Hall wave functions in C=1 continuum models. Okay, that's all I have. Thank you so much for the invitation again.
Thank you. Thank you.
Thank you.
Thank you.
So we are quite late. It's getting late, but I want to ask one last question as far as my questions are concerned. So if I don't start from K-space, if I want to try to, starting from the band structure, if I want to try to construct a real space picture, I would try to get Wannier orbitals. And one of the very unique things about twisted bilayer graphene at at magic angle is that the Wannier orbitals are very extended and they have this very non-local structure. So you cannot form a local model out of your AA and BB sites, but your Wannier orbitals are actually centered at AB, and they have these 3 lobes, right?
Yeah.
And that's a very different starting point from your low energy effective theory and starting momentum space, right? But that extended Wannier orbital is also a consequence of the band structure. So are a lot of things that you're talking about, this consequence of the band structure. So actually the next week at the same time, my student Kevin is going to give a journal club talk about our recent paper where we looked at if I start from that extended Wannier orbital and ask what interactions do, because I think of that extended Wannier orbital as giving me sort of a degree of freedom to work with, but I'm going to take the flat band literally and say that, okay, my kinetic energy is just turned off. Then that puts me into just extreme strong coupling limit, which is actually classical. So I can study a classical model of this extended object. And one very simple consequence of it is that because of the 3 sort of fractionalized lobes, right? This is not any fancy fractionalization. It's just like the wave function has 3 lobes. It's in effect, there is a third of charge per each lobe. You get an incompressible state at a 1/3 filling, 1/3 filling.
Oh, wow.
And the state has extensive degeneracy. And there are a lot of interesting and beautiful things about this model too, which is less known at the moment. So, I'm really curious. So that's the link to the paper, the preprint. I just put in the chat window, Zoom chat. I'm really curious whether one can make a connection between these very different starting points. And I was looking at your magnetic field. Of course, it is like changing sign between AB and AA, right? And we took the extended Wannier orbital as something that was given to us, but there are reasons why it had to be extended. There are reasons why it has that shape, right? And ultimately, they are all coming from the same kind of more microscopic model. That's the band structure that everybody started with. So but the way we formulated it, it's a very simple kind of physics, but it's an interesting state in the sense it's a charge order state at fractional filling.
Mhm.
but it's not a usual charge density wave because there is nothing modulating. Charge is uniform, just it's uniformly 1/3. And there is a lot of degeneracy because there are many different configurations. You have the whole very rich geometric problem, and there is extensive degeneracy. And I wonder whether it's at all possible to, we just took the interaction only, right?
Yeah.
To make connection between, what we found and sort of, starting from kinetic energy point of view, maybe there is a connection that's just disguised in different languages, or maybe they're totally different. I don't know. But, you can think of fractional quantum Hall effects sort of like as a charge order, the way Andrei Bernovic and others have formulated. This is not even that. This is very different. But now I'm kind of rambling, but this is just, I'm really curious because
Yeah.
I think of what we found to be quite pretty, but it would be really nice to see if we can understand this from low energy effective theory perspective too. Maybe it's not possible. I don't know. But if you're interested, you're welcome to come again next week.
I'd
We're
love
going to
to
be
hear
talking
about it.
about that.
Thank
All
you.
right. Any other questions?
I
Hi, can
have
you hear me?
sort of a.
No,
Go ahead.
it's okay.
No, you go ahead. Students are
Um,
encouraged to ask questions.
Hi. No, I just had some maybe some stupid questions, so hope you'll be patient. But in one of your first slides, you were talking about this like sort of the overlap between like a U of K and U of K plus 2.
Yeah.
I was just hoping you could remind. I was somehow under the impression that they should be like somehow orthogonal to each other. Could you enlighten me on
So-
what those actually are?
Sorry, let me try to get to the slide. Are you saying that because they're at different points in momentum space, they should be orthogonal?
Right. I mean that might be completely wrong. but
Right. So I think what you're saying applies exactly if you do psi k instead of uk. So
oh, okay.
yeah, if you do uk, that's like this overlap really comes from taking like say d2r psi bar k of r, and then adding in a factor of e to the I minus I q r psi k plus q of r. So this is the equality. So if we didn't have this e to the I k q, we would just have the overlap between two psis, and that would be 0. But this e to the I k I q r makes it not 0 and in fact equal to this.
Okay, great. Thanks. And my other question was I think you could explain again. And on the second last slide, with the dependence on kappa. I think what you were saying is that as as the sort of kappa increases, you go away from the chiral limit. Then you're sort of mixing in these remote bands and stuff. But why exactly did that break the analogy you made to the lowest Landau level?
Right. So I think in general, once you tune kappa away from 0, there's no longer this nice way of deriving the wave functions in terms of 0 modes of this operator. The wave functions are no longer 0 modes anymore. They have a small dispersion. And so there's the fact that there were 0 modes under this anti-holomorphic derivative operator, really that's what related them to the lowest Landau level, because that ensured that the essential dependence of the wave function was holomorphic. When you tune kappa away from 0, you lose that property. Another way to say it is that this trace condition is violated when you tune kappa away from 0. And that trace condition, by the results of Jer Wang is what's really responsible for having lowest Landau level physics.
Okay, okay, great.
Debanjan, you had a question.
Yeah, so I mean, I was just having this random thought. So if I was interested in the compressible composite Fermi liquid-like states at partially filled Chern bands,
Mhm.
I mean, here the energetics, etc., matters perhaps more sensitively. I don't know, but does thinking about it from this geometric point of view help us figure out where we might find it, or?
Right. So I think the way at least I think about these problems is I try to get as close to replicating the best lowest Landau level argument I can in the Chern band system of interest, if the Chern band is close enough to the lowest Landau level. So in the Laughlin state, there's a very rigorous argument in terms of pseudopotentials that it really is an exact ground state. I'm not aware of many like truly microscopic descriptions of the nu equals 1/2 state. And so I think that problem is much more challenging, but on general grounds, I would think that if we think it happens in the lowest Landau level and chiral twisted Bialy graphene is very similar to the lowest Landau level, I think there's reason to be hopeful. But it's hard to do anything better than that without something more microscopic.
All right, thanks.
Mhm.
Yeah, I have a question. So you spoke about the similarity of, of a generic band. Well, not generic, but when the inequality is saturated and when the Berry curvature is uniform. In this situation, it really looks like a Landau level, even though it may come out of other settings. Could you comment on the situation where I just give up the condition of uniform Berry curvature, but somehow I insist that I want to have the inequality saturated? Does it mean anything?
Right. So that if you just start with that condition and have the inequality saturated,
Yeah,
and you additionally restrict yourself to a Chern number 1 continuum model,
let's say that.
that's exactly what Jie Wang showed, is that you get lowest Landau level wave functions in an inhomogeneous field.
Oh, sorry. I see. Okay, that's I see.
Together with some like layer spinner or generic orbital thing that doesn't enter in the band geometry.
I see. So just saturating that condition tells me that I could always find some inhomogeneous magnetic field pattern in the space, and then somehow the band structure problem get mapped into this non-uniform magnetic field problem.
Exactly.
Ah, I see. Thanks.
Another interesting thing is that like this magnetic field really does behave like a magnetic field, because if you add like a flux quantum to a real magnetic field to chiral twisted bilayer graphene, then the real magnetic field and the inhomogeneous field add. And the wave functions are wave functions of the total field.
I see.
Sorry, I have a small question related to this slide. So what are the 3 lines with different colors in your plot?
Right, yeah, I didn't talk about that. There are different angles. So you can, what's true for every angle is that the Berry curvature and trace condition get much worse as you increase kappa. But you can somewhat mitigate this at a fixed kappa if you make your angle larger, in fact. So larger angles tend to be better for reducing the Berry curvature and homogeneity.
So you're saying that the 3 angles are near magic angles, or?
Yeah, I think this, yellow one is the chiral magic angle, which is 1.05 degrees with W1 is 110 MeV. So from there, I think go up in steps of like, I think the blue one is around, I need to check again. I think it's like 1.12 or something.
Oh, I see. Thank you.